Today what I want to talk about is some what is called as transients. So it's again a very big topic, but then today only we'll just, since you are just getting started, we'll only see very basic thing in that. And the question we are asking is something like this, which intuitively you might already know. So let's say there is a voltage, and then there is a switch, and then there is a capacitor. Okay. So this is pure capacitor, there is no resistance in this circuit. So let's say this is voltage is 6 volts, and then the capacitance value, let's say, let me check the actual value that I have, which is 100 microfarads. Okay. So the question is, at time t equal to 0, the switch S is closed. Okay. So before time t equal to 0, switch S was open, but at t equal to 0, S is closed. Okay. So the question we are asking is, what happens after you close that switch? Okay. So can someone guess what is the answer? What? Okay. So the answer I heard was, okay, first of all, if I close the switch, is the circuit complete? Is it a closed circuit? See, but if you see capacitor, there are two plates with insulating material in between. That's what is a capacitor. Can you still count it as a closed circuit? Okay. The answer is yes, you are saying. Then what happens? Will there be a current flow? And how much current? Very large current. Okay. Why very large current? Because there is no resistance. So these are, most of these things you already kind of know. And then what happens after very large current flows? The capacitor gets charged. Okay. So once the capacitor gets charged, what happens to the voltage across the capacitor plates? So the voltage will become equal to 6 volts. Okay. So what happens then after that? So the current becomes 0. What? Yeah. So current becomes 0 and capacitor acts as parallel capacitor, parallel to voltage. Okay. So far the answer that I heard was, if I close this switch, then the current goes and then it becomes charged, and then, so what is Q? Q is charge. Okay. So measured in coulombs. So it is nothing but C into V. Okay. So how much coulombs of charge is there on this, if for this circuit? C into V. So 6 into 100 micro. So 6 into 100 microfarads. So 6 volts into 100 microfarads. So that will become 600 microcoulombs. Okay. C is the symbol for coulombs, I guess. Okay. That much charge will be stored in this. Okay. So now if I want to see the point transients is that here we are worried about time versus how the currents will change, how the voltage will change and all. So that the study of that part we are calling is transients. Okay. So the current is 0, I equal to 0 before time t equal to 0. So before the switch is closed, the current is 0. After the switch closed, what happens to the current? So he said a very large amount of current will flow. Then finally the current is 0. So what happens? So there will be a spike, very high current, and then again current goes 0. Is that what happens? Current versus time? No. Then what happens? Yeah, it decreases exponentially, but for this circuit, because there is no resistance, so it suddenly falls also. It gets charged very fast. Okay. But in practical cases, here I am drawing the circuit like this, but in practical cases always some resistance will be there, and because of that resistance it is not able to, current is not able to reach 0 immediately. Okay. So to study that, we can always introduce some value of resistance here. Okay. So some value of resistance I'll introduce here. So now how does the transient thing changes? So let's say R equal to 273 kilo ohms. Okay, so that's a value I will want to use it. So now what happens? So to this drawing, before t equal to 0, the current is 0. Okay, S is closed and t equal to 0. Now I close the switch. Then what will be the behavior of the current? At S equal to 0, I close the switch. Then what happens to the current? What? Okay, so some of the answers here saying is, you see what is 6 by 270. Okay, then that will be the starting value of the current. Okay, it's actually correct. So what you do is, assuming that the capacitor is short circuited, see, because it is ready to get charged. So before time t equal to 0, that's also a given data that C is QC equal to 0 before time t equal to 0. That means it is initially not charged at all. And then what is happening? I close the switch. So you assume that this is a short circuit. So only Ohm's law, you can find out what is the current. I equal to V by R. So 6 by 240. How much is 6 by 240? So I'll call it I0, I0 plus. That means just after 0. 6 volts divided by 270 kilo ohms. So how much is this? How much? I need more decimals. 2 more decimals. Oh, okay. So into 10 power minus 3. Okay. So I'll write it 22.22 microamperes, isn't it? So just I'm converting into microamperes. Okay. So the current will jump to 22 microamperes, 22.22 microamperes. Then it will gradually decrease and then become close to 0. Okay, something like this. Okay. So at t equal to infinity, current actually becomes 0, but otherwise some current keeps on flowing. Okay. And somebody already mentioned this is an exponential curve. Okay. So what is the behavior of an exponential curve? The less charge that is there in the capacitor, the more it is interested to gain the charges. Okay. Or in other words, I can also say the more it is charged, the more it will don't want to charge. Okay. So like that. So whenever you hear that kind of statement, okay, the more it is, the more it wants, or the more it is, the less it wants, or something like that. Okay. So the solution will be an exponential curve. Okay. So I'll give you an example, maybe like dx by dt is equal to x. Okay. The rate of change of x with respect to time is equal to the magnitude of x itself. Okay. It's like somebody eating. Okay. So how much they eat depends on how much their weight is. So the more weight, the more you eat. But then the more you eat, the more you gain weight, and then you keep on exponential. That's this thing. So okay. So what is the solution for this? See, differentiate a function, you get the same thing. That's the exponential function, right? So what is d by dt of e to the power of t? Is nothing but e to the power of t only. Okay. Exponential curve is such that you differentiate it, you will again get the same thing. Okay. Or if you integrate it, you again get the same thing. So that kind of thing also is there. Is this correct? D by dt of e to the power of t is e to the power of t. Okay. Now here also we are finding a similar behavior. But but in a reverse way, that the less it is charged, the more it is willing to get charged, and the more it is charged, it is trying to oppose the current. Okay, so that's why initially current is high, and then so in that case, what kind of thing you can use? So I'll directly write the solution because I'm not that much strong in maths. I'll directly write the solution. What is I? So V by R, 1 minus e to the power of minus t by tau. Okay, I'll come back to what is the tau. Let's say t equal to 0. Is it correct? If t equal to 0, e to the power of 0, 1. So 1 minus 1 is 0. Then I think it's not correct. 1 should not be there. Yeah, okay, I think, yeah, this is correct. If t equal to, this is for I, so I was writing voltage of capacitor, then the 1 will be there. Or, yeah, something like that. So anyway, so I'll just write it neatly here. E to the power of minus t by tau. So if t equal to 0, then I is V by R, and as t increases, V by I decreases. Okay. So I can write it here. So what is this tau? Okay, time constant. Now you strangely observe, see, if I take a quantity R into C, okay, this is in ohms. I'm just doing units analysis. Okay, this is in ohms and this is in farads. Okay, what is ohms into farads? So it is strange that it is coming to seconds. Okay, how? See, what is ohms? This is nothing but V by R, V by I. So volts divided by amperes. Okay, 1 ohm is nothing but 1 volt divided by 1 ampere. Okay, what is farads? So I don't want to use that relation. I don't want to use this relation. So see, what is voltage of capacitor is 1 by C integration of I dt, something like this. The capacitor voltage will be the integration of current. This is the behavior of the capacitor. Okay, or in other words, what you can do? What is I? Or what is C here? C is nothing but like this. V here. I just interchanged V and C. Okay. So denominator volts are coming already. What is integration of amperes? Amperes into time. Okay. So the units of this quantity. So anyway, I know this is like farads. Comes in farads, but actually farad is just the name of the person. So which also, if I convert it, in fact, volt and ampere also names of the persons only, but ultimately you can go down, but we can cancel it actually. So volts is in the denominator, okay, and amperes is in the numerator into seconds, okay. Because of integration, it's multiplying by time. dt is the integration. So I can cancel amps and then I can cancel volts, and it comes to some seconds. So strangely, okay. So now if I consider, if I product of these two, 270 kilo ohms multiplied by 100 microfarads, okay, R into C, I'll call it tau. Because why I am calling it tau? Because it's in a seconds, maybe it is important value, okay. So 27 kilo ohms multiplied by 100 microfarads, okay. So kilo, micro and 3 zeros, I'll cancel out. Okay, micro is minus 6 and there are plus 3 0 and other 2 0. So finally I am left out with 27 ohms into farads, nothing but seconds. Okay, 27 seconds. Yes. Somehow tau is coming to 27 seconds. So what is the significance of this 27 seconds? What happens in 27 seconds? Yeah. So already somebody answered it. In 27 seconds, what happens is, so I'll write it. So let's say this is 27 seconds. I'll write it here. So from 0 to 27 seconds, the value will decrease. If this is 100%, it becomes how much percent here? 63%? 30, 63.2 is 1 and then 37.8, yeah. So while it is discharging, we'll use 37.8, while it is charging, we'll use 63 point. So time taken to charge up to 63.2% is the time, is the 27 seconds. So 27 seconds is significant in that way. Okay. So but why do we use this 37.8% or, so why not use 50% or, you know, see, first of all, we cannot use 100% because 100% means it will never charge, the current will never fall by 100%. Okay. Here it is 100% current, but it will not become 0%. Time is infinite, so we cannot use 100%. Then what other percentage can we use? Can we use 50% or 60% or 90%? Any percent we can use it. But it turns out that the formula is very simple because if you use this itself. So it's like reverse calculation. If I use 27 seconds, then what percentage it is? Then based on that, it turns out that 37.8% is the nice thing. Okay. So what is the definition of this time constant tau? Is that at 27 seconds, the current will fall to 37.8%. Is this correct? 37.8? 36.8, sorry. 36.8, anyway. Now, you can also mathematically see that, see, if t equal to tau, e to the power of minus 1. What is e to the power of minus 1? So, v by r into e to the power of minus 1 is 1 by e. Okay, you use your calculator, you type 1 by e, you will get 0.368. Okay, so e to the power of minus 1 is 0.368. So, v by r is the 22.22 microamperes. That's a full 100% current. By the time it becomes this much, the t has to become equal to tau, then it becomes like that. So, if I use any other percentage, it is the formula will be kind of little bigger. So, so that's why we use this 36.8%. Okay. So, this is all theory. So, the whole point what we are trying to say is it is gradually charging by introducing this R. Okay. So, now if I want to test this in the form of, you know, by building a network and then all these things, if I want to do that, what is needed? So now this is like, let's verify this whether it is really working or not. Okay. So how to verify this? So I need to make some table kind of thing. So maybe I'll use this place. So I want to measure the current. So time and then current. Okay. So 0 seconds, 5 seconds, 10 seconds, 15 seconds, 20 seconds, 25 seconds like this. Okay, 30, 35 seconds like this. Now every 5 seconds I want to see how much current is flowing. Okay. So expected. So what is the expected current? So this is 22.22 microseconds. Okay. So if I connect the circuit like this, 6 volts, 100 microfarad, 270 kilo ohms, and close the switch, immediately look at what is the current, expecting 22.22 microamperes of current. Okay, if everything is fine. Then gradually what will happen? 22.22 is what I am expecting. So this is let's call it measured, and then this is the expected current. Okay, so this is based on that formula. Okay, so at 5 seconds, how much current should be there? So I'll write it here. So I equal to V by R. This is nothing but this value, 22.22 micro. E to the power of minus 5 by 27. Was it 27? Yeah. So 27 is our tau, and then 5 is the, so I am substituting 5. Okay. So what percentage of it is it? So can someone calculate e to the power of minus 5 by 27? How much? Those who have calculator can try it. So first of all, what is value of E? 2.718. Value of E is 2.718. Okay. So why that special to why 2.718? Why not some other number as taken as E? So it is something. It's not a very simple question. It's something very, very interesting, very complicated or difficult or fascinating kind of question. Why E value should be only? It's like why pi value should be only 3.148. So something like that. So you try to think about it. Meantime, let's go with it. 2.718. Okay. See, the value of E is 2.718 because you are expressing it in a decimal system with 10 digits. So that E value may be something different. If you express it in maybe binary form, it will be something different. So finally, it's a value like that. Okay. So it's an answer for dx by dt equal to x. So it is something e to the power of 1. So something like that. Anyway, where am I? Yeah. So 2.718 to the power of minus 5 by 27. 0.83. So 22.22 micro into 0.83. So 83% of 22.22. So the current falls by 83% in 5 seconds. How much? Okay, so I am expecting after 5 seconds 18.4 micro. Okay, after 10 seconds, fast. Fifteen point four. 15 point? I heard 3, 2 and 4 also, I don't know. So you see, it reduced by almost how much? Near to 4 micro, but here it reduced by only 3 micro. So amount of reduction is also reducing. So can someone tell what is the current here at 35 or 30, whatever? See, at 27 I know what is the current, which is 36.8% of 22.2, which I don't know again how much it is. Okay, 6 point. So current is kind of reducing. So we get something like this. Okay. So what about the capacitor voltage? If I connect a voltmeter here, so how much voltage it will measure? Okay. So one very easy way to calculate this voltage, initially it is 0, agree, okay. A very easy way to do that is simply use this, see 6 volts is there, I into R is the voltage drop in the resistance. The remaining voltage will be capacitor voltage, whatever it is, okay. So 6 minus, so V minus I into R, okay. So what is I? This one. So V minus V by R into R, so R into V by R into e to the power of minus T by tau. Okay, so this is just by Kirchhoff's voltage law. Total voltage was 6, some voltage is dropping, remaining voltage is automatically the capacitor voltage. So this will be, if I take V common, 1 minus e to the power of minus T by tau. Okay, so this is my Vc. Voltage of capacitor is 6 volts into 1 minus this one. Okay. So when t equal to tau, this value will be 36.8%, but 1 minus 36.8% is 62.3%. So the amount of time it takes for charging. So what is the shape of this one? It starts from 0 and then it gradually charges to some value. So this is VC, voltage of capacitor. This is this white one is IC, current of capacitor or current of resistor or whatever. Okay, one is increasing, one is decreasing. So if I draw a line like this at 27 seconds, then this will be 63.2% of 6 volts. Okay, so we can also measure the voltage and then try to do that. Okay, so I just came. The class started at 10 o'clock or 10:10 I think. So I just came around 9:15 like that, and then we try to quickly search in the lab and then find some components and all. So you will find that the experiment we'll do will not match with this thing. Okay, so first we'll try to do this and then see why it is not matching, what might be the problem. Okay, so anyway, the pattern will be there, so we'll see. So maybe we'll switch over to this one. Switch over to the screen. Okay, we'll just remove everything. So what I am doing is, you can just focus on what you are seeing on the screen. So I have just this is 100 microfarads and this is R value 270K, the same thing that you see on board. So I am connecting R at the top. Okay, so this is my R, or maybe I'll just move it here. And then series with it I am connecting C. Okay, so R and C both are there. Now the next job is to connect the voltages. So maybe I'll just move it slightly. So we have voltages here. So where is my? So this is the plus of the voltage, and this is the other end of the voltage. Okay, so what you see, this one and this one are the voltages, 6 volts. So 4 batteries are there, each is 1.5, 1.5 into 4 is 6 volts. So you can see the 4 batteries there also. Okay, so I connect this R. Let me just, so what I did just now, I just short circuited a capacitor to discharge it if it was already charged. Something nice to always do. We'll look at that, what is it. So now I just want to reach from here to here. So now, so you see the entire circuit on the screen, except that this part is missing. So this is our switch actually. So if I connect this, the switch is closed. Okay. So obviously I'll use ammeter to close the switch. So I can measure the current and I can complete the circuit same time. Okay. So let's do that. I am connecting ammeter now. So let's not worry about the time for the time being. So something. Just a second. Yeah, so I actually disconnected my laptop's cable. Anyway, now we are back. So you can see 0. So I'll just maybe I'll just so the moment I short circuit, you can see 22, and then gradually it will reduce. Okay, we are not measuring time now, so hopefully it will work properly. So you can focus on the what happened? Let's do it again. It was working, but we'll just do it again. I just short circuit the capacitor. Okay, ready? So 21.8, then 21, then within 5 seconds it will go up to 18.4, okay, and then slowly reducing. Okay. So what is happening? The capacitor is getting charged, and the amount of charging current is less because it's already getting charged more. Okay. So 8.4, 8.1, 8.0, 7.9. Looks like it is working. In the morning it was not working. Okay. So this should go all the way up to, so after 35 seconds, it should reach 6.07. I think 35 seconds had passed. So now it is working. So even he is surprised who made the thing. Okay. So now let's do seriously. Actually, we'll take the measurement also. So can I have a stopwatch somewhere? It will be there in most of your phones. You have a phone? Yeah. So 2.7 current. What is that phone? So which one should you advertise? We'll go with iPhone. Okay. Looks like this is 5S. Maybe we'll just keep it here. So how do you want to do it? So we'll start the clock, and then maybe I'll just look at it every 5 seconds. I'll try to see what is the current and write it on board. Someone can help me with the number, okay? Or I'll not even look at that. I'll just look at the time only. So 1 milliampere. So maybe I'll just short circuit. I'll just repeat the whole thing again. I opened the circuit. Current is 0. Short circuit the capacitor. Okay. Now I'll restart the this thing. Okay. So why don't you start yourself? So maybe I'll just remove this directly. Okay, maybe I'll ask you only to do it because it's your phone. So what you do is this one you insert here and then start the time, both at the same time. Okay, keep track of time and then keep telling me how much is the value so that I'll write down. No, 1 second, stop. This should be visible on the screen. So you can few milliseconds you can do here and there. Yeah, so 21.2, 5 seconds, 18.2, How much? I'll keep going. 40 is 6.9. 45 is 5.1. 50 is 4.3. 55 is 3.7. 60 is okay. So shall we stop here? 1 minute. Yeah, we'll stop here. We'll take one after after a long time. We'll take one value. So yeah, you can just sit down. Maybe after 2 minutes we'll take a value. So we'll quickly make it a plot also. So I'll keep this running. I'll go back to Excel. So I hope you are able to see the values. So it's just nothing. I'm just so it's okay. Let's keep going. So 5, how much is it? 18.2. 8.1, 7, 6.9. So this is at 40. Okay, 45 is 5.1, 4.3, 3.7, 3.3. Now let's go back. We'll wait until 3 minutes maybe. So 3 minutes is 180 seconds, and the current now is 0.4 microamperes. Yeah, 0.4 microamperes. So here I'll put 180. Okay. Okay, now we'll do one more interesting thing. Now it is 0.3. We'll do one more interesting thing now. What I'll do now is, maybe you can turn to the board now. So hopefully when we plot, I'll get like this, and then this one mathematical you can see. I could have connected one more voltmeter and then measured the voltage also, but I did not, because of this thing, time I did not do that. So now what I'll do is, what is the current situation now? The situation is that the capacitor is fully charged. Okay, capacitor fully charged, and if I measure the capacitor voltage, it will be close to 6 volts. Will you agree that? Because the current is 0.4 micro, so that I into R will be very small, and then the most of the voltage will be at the capacitor. Okay. Now what I'll do is, I'll make a circuit like this. So there is no voltage, just that switch is. So at t equal to 0, S is closed. Okay. So what happens now? So here I'll say Vc0 equal to 6 volts. That means initially it's charged to 6 volts. Now if I close the switch, what happens? So this is already charged, so it will discharge. Okay. So this side was plus and this side was minus. So the current direction will be like this now, reverse current direction, and it will start discharging. Okay. So what is the initial value of current? When I immediately close it, the initial value of current will be 22.2 micro. Okay. And then how much time it will take for the current to become 0 again? See, finally the capacitor completely discharged, current will become 0. You should get exactly the same thing. Okay. So I stored charge in the capacitor, now I will discharge without the battery. Okay. So we should get exactly the similar this thing. Okay. So let's do that now. So again I will make a table. This is for discharging. Will it be exactly same or will it be slightly different or whatever? So we'll see. So again 0, 5, 10, 15, 20, 25, 30. 55, 60, and then maybe after a long time we'll see. Can you switch on the clock? How much time is it? So 180 seconds, 0.4, and then maybe it is now 5 minutes, 6 minutes. So 360 plus how much? 380 seconds approximately. So and what was the current? Point. It's jumping towards 1. So you stop the clock. Okay. So 0.15 microamperes. Okay. So now let's. So you can come back to this one. We'll just focus only on the screen, but then I'll just write down on the board whatever you tell me. So you can only on this screen. Okay, so what I'll do now is I'll just disconnect, I remove the ammeter so the current becomes 0, and then I'll just also remove the voltages. So there is no voltage in the picture. Only two things on board. One is R and one is C, but be careful, the C is already charged to a very high voltage of 6 volts. Okay. Maybe quickly we'll measure the voltage. So I'll just go back to voltmeter measurement. So but the problem is the act of measuring the voltage of the capacitor itself will result in capacitor losing some of its charge. So we'll just quickly measure and then come back. Okay. So volts, I have to change this connection. Okay, what you are getting is just some normal values. So now it is 0. So let's measure the voltage of capacitor. Okay, just quickly and then we'll go back. How much is it? So 5.92. If I stayed there, it would gradually discharge also, but then we don't want to discharge it. So the voltage was 5.9 something. So which is what is expected. So now I'll just connect like this now, including the resistance. So I'll go back to ammeter, go back to microamps, 0 microamps. We also need the time, so just unlock it. So to get negative reading, I'll connect it like this. So yeah, insert it and then start. So every 5 seconds I want what is current. Okay. So 21.3. How much? 10 seconds, how much? 15. 20 seconds. 5. 5.9. 45. 50. 4.3. 55. 3.6. 60. So we'll just now wait for some more time. So yeah, so we got some values. Looks like, we'll switch back to the board. Looks like both are same, so what is the equation for this? What is the mathematical equation for this circuit, which we just have on board right now? So let's write Kirchhoff's voltage law. No, you can leave it. Yeah. Kirchhoff's voltage law. Okay. So let's take this point. Okay. So from here to here, you can assume any current. So let's say the current is like this, or any direction of current. So what will be? Or I'll say this voltage plus this voltage is equal to 0. Okay. So I into R. Okay. I into R is 1 voltage plus, what is the voltage of this one? What is the voltage of capacitor? 1 by C integration I dt, okay, is equal to 0. So these two voltages should be equal to 0. Okay. So because this integration symbol is there, I am scared a little bit. So what I will do, I'll just differentiate both sides. Okay. So di by dt, okay, is equal to I. Okay. Now I am little bit now if I write it, I'll write it like this: di by dt is equal to minus I divided by RC. Okay. So the rate at which, see, di by dt is rate of change of this one, okay, but because of minus sign, I will say the rate at which it will fall, the rate at which current will fall. Okay. The rate at which current will fall is nothing but the current value itself divided by this some constant of proportionality, whatever. Okay. So if I is more, it will fall faster, and if I is less, it will fall slower. So that's what you are seeing now. So because it was 21.3, it fell to 17.8 in 5 seconds. But by the fact of falling to 5 seconds, then the next time the amount of decrease is less, the next time amount of decrease is less, and all these things. Okay. And this is the same thing, which dx by dt equal to x kind of thing. Okay. Dx by dt equal to x is more like, the bigger you are, the more you gain and all. This is like the higher value is there, it becomes smaller by that much. Okay. Okay. So see, I can always do one thing. I can always take a calculation and then match it with the measurement. Okay. So we still have time. So let's do that actually. So how much time now we have? This is 4.5, 0 milliamperes, completely discharged. Okay. So what is that? 4 into 6, 240, 280. No, 270 seconds. Okay, 270 seconds it reached to 0. It's actually still some current is flowing. Okay, but our measurement is not able to measure that much current. It's not still 0. It will become 0 at infinite time, but we are not able to measure it. So that's why. So at 5 also it is 0. Okay. This itself got frozen. So shall we match experiment with calculation? With that we'll finish this part. So I'll write it calculated here. So can you just focus only on this one? Yeah. So what is the calculation for value of I? Okay, V by R. So let's introduce the parameters also. Let's say VR, V was 6 volts, R is 270K, and C is 100 micro. Sorry. (100 E minus 6). So this is our parameters. So is equal to this divided by this exp minus t. So this one divided by tau RC. So R into $E$2. I don't want to complicate it. We'll just do like this: 22.2 1 minus into exp this divided by 27. No, this is for the first one, the charging. Okay. Minus, minus t. No? So let's, how do we plot this? Insert object charge chart. Finish. Okay. So I hope you are able to see both. I think it's quite visible. So the blue line is measured, and then the red line is calculated. So it is matching. Now why it is this? I think at 40 this one it was 5.9. Okay, so let's change the data. Normally we do this while doing experiments. Yeah, because I just was in a rush, so I did not note down properly. So the measured one just got covered. So this is what 5.9 you want? Still it will not be correct, no? But anyway, yeah. So shall we do the other one also, or it's not useful to do that now because we already understood the thing. So yeah. So maybe we'll come back to the board. We'll leave it here. So what are the applications of this? What are the applications of having a circuit like this, slowly charging, slowly discharging? So that is one thing we can take up maybe later, but in the meantime you can also find out. So in the meantime I'll just talk about only through, we don't have the circuit elements for that. Just look what happens in this case. Okay, sorry, it's a DC voltage only. Switch and the inductor. Okay. So let's say 10 ohms, and let's say make it 2 henries. Okay. See, the problem is 2 henries is a very large this thing. You cannot have a small thing like this and then it's 2 henries. It's a very large this thing. The biggest inductor we have in our electronics lab. So was about 100 millihenries. Okay, so and 2 henries is quite large. So, but still, if you want to do experiment with it, so let's talk about time constant. Okay, so RC time constant is nothing but R into C. But in this case, what is the time constant? So time constant tau is L by R. Is that correct? Let's verify it. Okay, what is voltage of inductor? L di by dt. Okay, inductor voltage is nothing but L into di by dt. Okay, now I am interested in current. Okay, so time current. So t equal to 0, switch is closed. Okay, what happens then? At t equal to 0, if you close the switch, what will be the current? The current will remain 0 and then goes on to increase to what value? So let's say this is 6 volts, V by R, 6 by 10, 0.6 amperes. Okay, and by, so I think, sorry, the shape should be like this. So by your tau, so this will be 63.2% of 0.6. Okay. Now the units we were talking about. So here the units is volts. Okay. Here the units is amperes by time. Okay. So this is henries. Okay. So volt equal to Henry into ampere by time, seconds. Okay. So what is Henry? Volt into second by ampere. Okay. So now here volt second by ampere, and what is the unit of resistance? Volts by amperes. Okay. So volts by amperes. So amperes will cancel, volts will cancel. So I'll get time in seconds. So L by R is the time constant for this one. Okay. So in this case, what is the time constant? 2 henries divided by 10 ohms. Okay. So 0.2 seconds. Okay. So within 0.2 seconds it will do. But I want to demonstrate in the classroom. So I want 1 minute time or 2 minutes time. Okay. Then the problem is more severe because I need to get, larger value of L. Okay. So it's we don't have that. But the problem is I can use smaller value of R, 1 milliohm, 2 milliohms like that. But that is also a problem because it results in a very large amount of current. Okay. So when the R is very small and if I use 6 volts, so like if I use 1 ohm, it will be 6 amperes, and 6 amperes is too huge current. So you are seeing we are measuring microamperes. Okay. So because of that practical reasons, I am not showing you the LC circuit, sorry, RL circuit. Okay. But mathematically we can always do this calculation. Okay. So let's write it then. What is I? So what is the value of I? So the final value of I will be this one, 0.6 V by R. This is the final value of I, and the initial value should be 0. So it will be 1 minus e to the power of minus t by tau, or which is L by R, something like this. Okay. So if I substitute t equal to 0, so this I will be 0, and if I substitute t equal to infinity, e to the power of minus infinity is 0. So V by R is the current. So that's nothing but 0.6 amperes. Okay. Now in this also, what happens is when the infinite current is flowing, then if I disconnect this and then connect it to another switch, okay, then what happens? Then also there will be a reverse current. Initially the current will fall like this. and then it will gradually become 0. The inductor is discharging. Okay, so inductor stores energy in the form of magnetic field, and the capacitor stores energy in the form of electric field and all these things. Okay, so this is what, see, because I thought it was important to cover this thing about how it will charge and discharge. So that's why I took the entire class on that. But still there are so many things which are left to be told and all on this, but you got the main points, I feel. So just to cover some more time on this. So if I give you, just to extend the discussion to another level, if I give you a big circuit like this, something like this, I'm just you know, so how many switches are there? So we'll put one more switch here. And put a voltage here. Okay, something like this I'll give. Okay, so S1, S2, S3, S4. Okay, so let's say 10K, 20K. Okay, this is 50K, and this is 90K. This is 20 volts. So this is 30 volts, and this is capacitor only. Okay, so let's say this is 100 microfarads, and this is 200 microfarads, and this is 300 microfarads, or something like this. Okay, this is a big circuit. Okay. Now, if I say something like events, okay, so t equal to 0 minus, okay, before you start the experiment, okay, t equal to 0 minus, let's say S1, S2, S3, S4, okay, all of them are maybe I'll close 4 and 3, and 1 and 2 I'll keep it open, something like that. Okay, so close, close, open, open. This is my before the time t equal to 0. Okay, so then what I'll do is maybe at t equal to 1 second, I'll close this, and then I'll just do like this. See, I can do anything. I can do infinite different kinds of things. Okay, so and then at t equal to 1.2 seconds, I'll close this, I'll open this, and close this, something like this. So these are my events. Okay, so with respect to all these events happening, given the data of voltages, capacitor values, resistances, and their network connections, okay, you should be, with what we have discussed, you should be able to tell, like at any given time, what will be the current in, like let's say 10 kilo ohm resistance, what will be the voltage in this one, what will be the, how much is the charge stored in each of this thing, whether it is plus or minus or plus, whatever. So all these things you should be able to calculate based on just what we discussed. Okay. Of course, you will have to write a nice software, elaborate code to do this kind of thing. But what I am saying is, based on what you just saw, that one equation, you can develop something like this for this to happen. And then where do the events come from? So events can be something like you have a nice screen, and with mouse I can just click on the switches. So I click this switch, it will open, it will become closed. If it is closed, it becomes open. And then immediately taking that information, you can always do all that kind of calculation. So, so in principle, you can do all that things. Okay. So if you want to take it as some kind of a Sunday afternoon kind of project, you can do that. So, but even without doing all that, you should have an intuitive feel what is going to happen. Okay. So you can always see what will be the time constants involved, and then how it will, which one will charge, which one will discharge, these kind of things. Okay, so think about this. I am not giving you any answer. This is just this is not even a question. It's just a this thing. I'll just leave you with another thought. Maybe if possible, we'll try to find out a way to demonstrate it. So I can build a circuit like this. So with a switch here, or the switch can be like this. Okay. So this is R1, this is R2, and then this is C. Okay. This is easy actually. So when the switch is in position 1, you are charging. When you change the switch from position 1 to position 2, you are discharging. Depending on the value of R1 and C, the charging time constant will be there, and depending on the value of C and R2, the discharging time constant will be there. If you use a small value of R2, it will quickly discharge, and so on. Where it becomes interesting is, instead of using R2, you can use L here. Okay. Then what happens? So here you are charging, and then you change from 1 to 2. Then what happens? So will this discharge or not? It will discharge, and then the current will start flowing in L. Okay. So what will be the equation for that current? So it will be a sine wave, because there is no resistance. It will be a sine wave. So this will discharge, this will charge, then this will discharge, and this will charge, and all these things. So you can mathematically do it. You can also connect it and do it. In case if there is a resistance, then what happens? So it will be a sine wave, but the amplitude of the sine wave gradually reduces. So it will be something like this. So sine wave with reducing amplitude, something like this. Finally, the current will become 0 in this when the switch is changed to 2. Yeah. So, and if you draw like this will again be that exponential curve. We'll come to it. We will maybe in later classes we'll see some of these things. Okay, but you think about what we have covered today. So I will stop here. So regarding your papers and all, I'll